Here's the story so far. Our ultimate aim is to differentiate y equals a to the power of x. But whenever we try and differentiate this here, we would get some sort of constant times a to the power of x. So what's happening here is that whenever you differentiate something to the power of x, you will get this block times itself. Remember that this something here will affect this block, and it will also affect this one here. So we would try and search for a constant where when you differentiate it, this whole thing here will equal 1. Because what it means is that if you have this here and then you differentiate it, and this being 1, it would mean that dy by dx will be itself. So what's happening is that we are trying to search for a constant here so that it would make this block here to be 1. When this block here equals 1 here, what it means is that when you have this thing, and then if you differentiate it, you would get dy by dx equals itself. Nice and simple. So our aim here is to try and seek out this number here, this constant here. And we know that this constant here exists somewhere in between 2 and 3. Okay, so it exists. Well, we don't know precisely what this constant here is. So for the time being, we're just going to say it exists. And let's just, for the time being, let's just call it E. Okay, so what that means is that if you have some y equals e to the power of x, remember we don't know precisely what this e is. We're just going to call it e for the time being. So when you differentiate this here, dy by dx will be itself. Okay, because we deliberately went out and try and seek for a number here where it will make this here to be 1. That's all that we're trying to do. We are just trying to make this here to be 1. Okay, so far, hang on. So far, we've got a function here, e to the power of x. When you differentiate it, it will be itself, meaning that the gradient here. What we know about e so far is that if you try and differentiate this here, the gradient at x equals 0 here, the gradient right here will be 1. That's a property of our special number e to the power of x here. Okay, and then well, whenever you have a function, you can always in a way manufacture the inverse of that function. So we came up with this function here, and then we manufactured this function here, the inverse version of this. So whenever you remember from our section on functions, whenever you have a function, you can always create the inverse by reflecting it along the y equals x line. Well, anyway, if the gradient here is 1, then the gradient here will also be 1. And well, at the moment we've in a way made up a function e. Well, we've created a function e to the power of x, and from this we in a way manufactured the inverse version. And then we would, because this is quite important here, so we would give it a special name, a natural log of x here. Okay, so hang on. So far, we've got e to the power of x. We manufactured the inverse version, and we're going to call it the natural log of x. Now, here's the thing. Our aim here, our aim now, is to try to differentiate this natural log of x. So we came up with e to the power of x, and then from this, we in a way manufactured the inverse version. So in this video, we're going to try and find the gradient, the derivative of this line here, because our ultimate aim is to try and find out the derivative of a to the power of x. But in order for us to do this, in order for us to find out the derivative of this, we would invent e, and then invent this natural log, and then now we need to find out the derivative of this, just so that later on we can find out the derivative of this. Well, anyway, in this video we're going to try and find out the derivative of this. Okay, so let's start out with this. So our aim here is to try to differentiate. Actually, I'm going to do this in the next video. Okay.